Welcome back, students. In this lecture, we will discuss the topic strain energy due to bending moment. Okay. Bending element such as a beam, the bending moment varies along the length, so as the curvature of the beam also varies along the length, right? So, in order to calculate the strain energy due to bending, we can say that it is nothing but the area under the bending moment versus curvature curve, which is nothing but area for this triangle, half into m of x into phi of x. We also know that m is not a constant, so it varies along the x, so we give it as m of x. Also know that the curvature is also not a constant, it varies along the x, so we say it as phi of x. Okay, so this is for a particular one section. So in order to get the total bending moment, we have to integrate it from 0 to L along the x direction. So the expression becomes half, which is a constant, we take it outside, half into integral 0 to L m of x multiplied by phi of x dx. Okay, so also we know that from the bending equation, m by I equal to sigma by y equal to e by r. Okay, so this phi of x, which is curvature, is nothing but inverse of the radius, which is r, right? So phi of x is nothing but 1 by r of x, right? So we also, from the bending expression, it is clear that 1 by r is nothing but m by ei. So we can say that phi of x is nothing but m of x divided by ei, right? So substitute this phi of x as m of x by ei. We have the expression for bending strain energy due to bending as half of integral 0 to L m of x square by ei dx. Okay, this expression can also be written in terms of phi of x, which is looks something like this. Okay, so usually we use only this expression for calculating the bending strain energy due to bending. Okay, now let's see a small derivation. So consider a beam of length L and width B and depth D. Okay, out of that we consider a small elementary volume of width, which is width B, which is same as that of the beam, and elemental depth dy and elemental length dx. Okay, we can say that the volume of this elementary volume is nothing but b into dx into dy, volume of a cuboid, right? B into dx into dy, right? So from previous lessons we already knew that the expression for strain energy is nothing but sigma square by 2e multiplied by volume. So we use that same expression here also, sigma square multiplied by v divided by 2e, right? So here volume is b into dx into dy, and also what is sigma? Sigma here should be the bending stress, which can be found out from the bending equation as sigma is equal to m by y multiplied by I divided by I, right? So you can substitute instead of sigma as my by I. So we have an expression something like this. From here we take out all the constants together, so we have m square by 2ei square multiplied by y square into b dx dy as the strain energy for this small elementary volume, right? Which is shown in the dark black lines. Okay, now if you want to calculate the strain energy for this bigger cube, which is shown in the green dotted line, what you have to do is you have to integrate it along the y direction, right? So if you integrate this expression along y direction, okay, integral 0 to d, you integrate this expression, what happens is you will get the strain energy for this entire big cuboid, which is shown in this dotted green line, right? So we have u is equal to integral 0 m square by 2ei square into y square into b dx dy. So we know that b into dy can be written as area, breadth multiplied by depth is nothing but area of the side, right? So we can say that this is dA, area of the elemental length. so area of the elementary object, right? So we have an expression y square into b into dy, which can be, this b into dy is nothing but dA, then integral y square dA is nothing but I. So instead of y square b dy, we can substitute it as I, and I and I get cancels. So what remains is u is equal to m square by 2ei dx. So this is the strain energy for a volume which is shown in this green dotted line. Okay, now if you integrate this strain energy along the length x, okay, you will get the total strain energy for the entire volume of the beam, right? If you integrate along the x, so what you have to do, again you have to integrate from 0 to L m square by 2ei dx. So this will be the final expression for the total strain energy. So this limit will be 0 to L. Fine. So that's it. This is how you will calculate the strain energy for due to bending moment. Okay. We have problems related to strain energy due to bending moment. So read the problem carefully first. Find the strain energy in the beam of length span L, and hence find the deflection under the load. Strain energy due to shear may be neglected and assume constant EI. Okay, so here we have a simply supported beam with a load which is eccentric from the center at a, it is at a distance of A from the A support and B from the B support. Total length is L. Okay, so if you try to draw the bending moment diagram, it will look something like this, which means that bending moment, when you have to draw the bending moment diagram, it has to be divided into two parts. Okay, so first we have to consider a section somewhere here, so x will be considered as this, and secondly for the second section you can consider this is x4 first, we can say it is x1, and then we have to consider another section at a distance of x for writing the bending moment expression for section CB, right? So before doing all these things, you have to first calculate the reaction at A and reaction at B. So if you take moment at A equal to 0, we have W into A is equal to RB into L, which means that RB is equal to WA divided by L. And if you take the moment at B equal to 0, we have WA into B is equal to RA into L, which means that RA is equal to W divided by L. So we wrote what is RA is WB by L, and what is RB, it is WA by L, which you can easily find out. Okay, now if you want to write the expression for bending moment for the section AC, consider a section at a distance of x. Okay, so you can say that for this particular section x, at x, the bending moment is equal to WB by L into x, right? So for section AC, m of x is equal to WB by L multiplied by x. So we again use the usual bending moment sign convention also, which is on the left clockwise moment is taken as positive. So we have clockwise WB by L into x as moment. So mx is WB by x into L for the section AC, and x varies from 0 to A. Okay, now for the section CB, we will consider a section away from C at a distance of x from A. Okay, so for section CB, we have, if you consider section here, on the left we have two forces, on the right we have only one force. So it is easy to calculate the bending moment on the right, which is nothing but W RB multiplied by, what is this much length, this is nothing but L minus x, right? So RB multiplied by L minus X. What is RB? WA by L. So WA by L into L minus X. This is the bending moment at this particular section. Okay. So here you can see that X will be varying from, for the section C to B, the X will be varying from A to L. So for X varying from A to L, the expression for Mx is WA by L multiplied by L minus X. Now in order to find the total strain energy, you have to calculate the strain energy for the first section AC, and again add to that the strain energy for the section CB. Right. So for the first section, strain energy will be integral 0 to A WB by X, sorry, WB by L multiplied by X the whole square into dx divided by 2EI, plus for the second section the Mx is this much. Okay, so M square, find the square of this, multiplied by dx divided by 2EI, and the integration is X is varying from A to L, so integration from A to L. So solving and substituting, finally we have the expression for total strain energy as W square A square B square divided by 6EIL. Okay, so this is the total strain energy of the beam. Clear? Now we also have the question to find out what is the deflection. So this strain energy is actually the energy stored in the beam. So what is the work done on the beam? So we have only, right, which is at W, and the beam as a whole deflects something like this, right? So let's say there is a deflection of delta C at C, or YC at C. So the work done by the load on the beam is nothing but work W into YC deflection divided by 2, because this is gradually applied, right? So half into W into YC is the work done on the load. So this is work done on the load. The work stored in the beam is nothing but strain energy, which we already find out. So we can equate them each other. So half W into YC is equal to W square A square B square by 6EIL, which is nothing but the strain energy of the entire beam, right? So from here we can find out what is YC, or deflection at C, right? So we get deflection at C, YC is equal to W A square P square divided by 3EIL. So this method of finding the displacement is called as strain energy method also. Fine. We did nothing. We know that strain energy is nothing but the energy stored. So we have to find out what is the work done on the beam. So work done on the beam is nothing but the work done by the external load, which is load multiplied by corresponding deflection divided by 2. Okay. Again we have one more problem here. Using strain energy method, find the deflection at free end of the cantilever with point load at the free end. Okay, simple question. So what you have to do here is, first of all we have to find out what is the total strain energy of the given beam. Okay, for that, first of all you have to find out what is the reaction. So reaction here is P, and there will also be a moment which is PL, right? Then we have to draw the bending moment diagram. The bending moment diagram will look something like this. Okay, now consider a section distance x from support A. So the remaining distance is L minus x, right? This much distance is L minus x. Okay, what is the expression for bending moment? Mx. On the right hand side of this section we have only one force, so that is P. So P into L minus x, which is clockwise on the right, which means Mx is negative. So Mx is minus P into L minus x for x varying from 0 to L. So this is the expression for bending moment. In order to find out the strain energy, U is equal to m square by 2ei into dx. So you have to integrate it. What is m? It is minus b into l minus x. So we have to integrate this particular expression, p square into l minus x the whole square. This was nothing but m square into dx by 2ei. So integrate from 0 to l. We have the expression for strain energy as p square l cube divided by 6ei. So this is the total strain energy of the entire beam. Okay, we also know that the deflection of this particular cantilever beam will be something like this, right? So we have a tip deflection of, let's say, yb. Okay, so the total energy stored in the beam is strain energy, which is equal to p square l cube by 6a. Work done on the beam is nothing but p into yb divided by 2. So work done on the beam is half into p into yb. Work done should be equal to work stored or strain energy. So we equate it both the expression each other and find out what is yb. Simple. So we get expression for yb is equal to pl cube by 3ei. Fine. Thank you.